Hello. Today we're going to talk about our time series project exploring the Texas COVID-19 case data. My name is Anna and my partner is Cameron. Today we're going to talk about our project, the data that we explored, the variables that we modeled, and the models that we developed. The stakeholders of our project are the Texas government policymakers. Our objective is to develop a forecast for both short-term and long-term COVID cases. Our purpose is to enable policymakers to make informed policy decisions. The data we explored is the COVID-19 case data, the vaccine doses administered, the COVID tests taken, and the Google mobility data.
Next, we'll explore our variables. Our target variable is the COVID case data. And as we can see here, the data appears to be wandering. And you can see this in the spectral density with a peak of 0. The data also appears to have a possible seasonality of 7 days, as this is daily data. And we can see that in the sinusoidal activity of the ACF. We will conclude that this data is not stationary. Looking at the regressors, in the top 2 charts, we see the COVID tests administered and the vaccines administered. And we can expect that these will have an impact on COVID cases. On the bottom, you see the mean mobility data. This is using mobility data from Google compared to a baseline that's been taken historically. And at the start of the pandemic, you do see a dip as you'd expect, and it has slowly started to return back to normal. And these are divided into different categories that are shown in the bottom left. Next, we'll look at the ARIMA models that we made to predict COVID cases. The first model we looked at was a seasonal model. We removed the seasonality of 7 days from the initial realization of COVID cases, as we saw in the spectral density. This was plausible, and this did appear to stationarize the data and had remaining autocorrelation. Using an ARMA 21.8, we accounted for this residual autocorrelation, and we were left with white noise, as shown in the bottom right plot. The second model we used was a differencing model. We removed the 1 - b term, and we did stationarize the model, and we were left with residual autocorrelation again. We used an ARMA 614 model, and this accounted for that residual autocorrelation, and we were left with white noise, as shown in the bottom right. Comparing these 2 models, we can see that the differencing model outperformed the seasonal model in both the short-term and long-term forecast by using a rolling window RMSE. Next, we'll look at vector autoregression models. The first model we'll look at is where each of the variables are difference with a 1 - b term, and we also use a constant term. The second model uses a seasonality of 7 days, and differences only are response variable cases. We also looked at multiple other VAR models, but we've only included the 2 most useful models we identified. There is a lot on this page, but I want to show that in the top left, we use the var select function to identify a lag of 7, which had the lowest AIC and BIC. Using a var 7 model with our model 1, we see on the right the significant coefficients of the variables for each of the lags. In the bottom left, we can see the prediction interval resulting from fitting this model. For the second model, we once again performed a similar procedure. We used var select to identify a lag of 8, which had the lowest AIC and BIC, and we can see the significant coefficients for our predictors, and we can also see our prediction intervals for each of our variables. Comparing the results of model 1 and model 2, we have a split decision. So the first model we looked at without the seasonality had a lower long-term RMSE. And the second model we looked at with the seasonality had a lower short-term RMSE. So looking at AIC and BIC, model 2 was lower in both categories. So we will say this is our preferred model.
Now let's look at the multi-layer perceptron models. The first model that we developed was only based on the test data and the vaccine data. We developed a model with 5 hidden nodes and 20 repetitions and noticed that our target variable was lagged by 4. A regressor variable that was included was lagged by 3. Looking at our second model, we developed the MLP model based on tests, vaccines, and Google mobility data for parks and recreation. This model was also fit with 5 hidden nodes and 20 repetitions. We noticed that our target variable was once again lagged by 4 lags, and 2 regressors were included, one with lags 1, 2, and 3, the other one with only lags 1 and 3. When comparing these two models, you will see the repetitions are visible in the light gray lines, and our actual data is the blue line. When you look at the model that is developed only using tests and vaccines compared to the model of tests, vaccines, and mobility, it is obvious that the mobility model is a lot more closer to the actual data than the model that does not include the mobility data. In conclusion, the short-term and long-term RMSE for the model with the mobility data is lower in both cases. When we look at our ensemble model, the gray lines that you see here are the VAR model and the MLP model that we selected as the best as part of our first analysis. When we took these two models and we calculated the mean, we called this the ensemble model. The ensemble model had a better RMSE for both the short-term and the long-term forecasts. When we add a little bit of history to put this into context, it is obvious to us that the ensemble model does a much better job at predicting the peaks and valleys for the COVID-19 cases. When we summarize the RMSE for all of the models that we selected as best in each particular category, we conclude that the ensemble model has both the best short-term and long-term RMSE, so we feel confident with our selection. So what are the next steps? We have concluded that the ensemble model that picks the VAR with seasonality plus the MLP model that includes mobility data is our best model. This model can be published as a public service dashboard that can be used by both the public and the policyholders. This model could also be considered to predict capacity requirements to plan for hospitalization and available ICU beds. We can't wait to see this model in action and giving people more information about the predictability of the COVID-19 cases based on vaccines, tests taken, and mobility data. Thank you.